Okay, hi everyone. Welcome to the Graphs and Matroids seminar. Today we have Mehtaab Sawhney, who's going to be talking about enumerating matroids in linear spaces. Oh, and he's from MIT. Go ahead, Mehtaab.
Yeah, thanks for the introduction. So I'll be discussing enumerating matroids in linear spaces, and everything I'll be discussing today is joint work with Matthew Kwan, who is at IST Austria, and Ashwin Shah, who's another graduate student with me at MIT. So let me define a matroid, although I think most people in the audience are more familiar with these objects than I am. So we say a subset of subsets of a ground set E form the independent sets of a matroid if one, you have the empty, one of your subsets is the empty set. Two, if A prime is a subset of A and A is independent, then A prime is independent. And three, suppose you have A, which is smaller than B in size, and A and B are both independent. Then there exists E, which is part of B set minus A, such that A union E is independent. So I guess the canonical example of a matroid is always given a subset S of vectors, the subsets which are linearly independent. So this is more definitional. And so the problem we'll be concerned with today is sort of given a ground set of size n, how many matroids are there? And so let Mn be the number of matroids on a ground set of size n. So I mean, I've just defined a matroid, and you can already define the problem of interest. And it turns out this is actually, in and of itself, a very difficult problem. And we know some things, but we don't actually know the answer. So in particular, so we only have control on the log asymptotics of M of n, which is a pretty crude level of control. So the best lower bound, so this is an explicit construction due to Knuth, tells you the log is like n minus 3/2 log n minus little 1. So this is due to Knuth. And the upper bound, so this is quite old. This is from the 70s, I believe. And there was recent, really amazing work of Bunsel, Pendeven, and Vanderpoel, which gives an upper bound which matches this up to an O of 1 in the log asymptotics. And this is much more recent, I believe 2015, if I remember correctly. And so this is an explicit construction, and the upper bound is roughly using this method of graph containers. And in this final paper, they sort of point out that if you want to do better than this like O of 1 gap in the log asymptotics, you would need to understand independent sets in the Johnson graph, which is a notorious coding theory problem. But so given this, and given that we don't really, if you look at their proof, this tells you that it suggests that most Matroids have rank around n/2. Given that, it's sort of natural to consider Matroids of a fixed rank. So, so in particular, the question we'll be concerned with is slightly more specialized. It's given a fixed rank. So the rank of a Matroid M is the size of the maximum independent set. And so now the question is to enumerate M and R, where this is a ground set of size n. And rank R. And for the purposes of this talk, we're not going to consider R growing, we're going to consider R a fixed constant and n growing. So the first two cases of this are, well, the first case is easy enough. Mn1, so this is the number of Matroids of rank 1. So this just means that you have a bunch of singletons in your as your independent sets, and you can't have no elements in otherwise you would be an empty Matroid. So you can, it's essentially a trivial counting exercise that this is exactly 2 to the n minus 1. And a more involved but also relatively direct argument set tells you that there's an exact formula for mn of 2. So this is bn plus 1 minus 2 to the n. So this is the Bell numbers, and there's some correction, and I believe this was first observed by Aketa in 78. And more recently, so given this, it appears for larger R, there isn't some exact formula like this. So the question is, can you get asymptotics? And here we're not going to be concerned with log-log asymptotics. That's too crude. Really what we'll be concerned with is the log asymptotics. And here there's a theorem of van der Hofstad, Pendeving, and van der Pol, which proves this for all R bigger than 4. So their precise result is the following. So they give a precise asymptotic for the logarithm of mn of R. So it's some funny formula. And they derive this ultimately from work of Kibosh on enumerating designs. But this also relies on earlier work of van der Pol and Pendeving, which I'll mention because that will be relevant later. So given that I've mentioned designs, okay, so let me now just state the main result of this talk, which is, given that we know R less than 2 and R bigger than 4, there's kind of an obvious question: what happens at R equals 3? And the main result of our work is to close this gap. So the main theorem I'll be discussing today, so this is joint work with Matthew Kwan, Ashwin Saw, and myself, is that mn of 3 is some ugly number. It's 1 plus square root of 3 over 2 some fraction, some number times n plus a little n to the n squared over 6. So it's some number. And notice that for R equals 3, if you look at the previous result and you plug it in, it's not the same number. So something slightly different is happening. And really, although I phrase this as a problem about Matroids, there's actually a really beautiful reduction due to these two authors, which turns this more into a problem of counting something, which counting what is called clique partitions. So given that the techniques we have in our paper can handle all R, all fixed R, but I'll focus on R equals 3 as that's the only new case. So And so due to a reduction of Hindving and Vanderpoel, it suffices to instead count the following objects. Count PNR, which is the number of paving matroids. On n elements. And the reason I got interested in this problem is that they sort of, in the earlier work, they point out that PN3 has a sort of very nice and simple non-matroid definition. So you take Kn, so this is the complete graph on n vertices, and cover Kn with cliques, which are edge disjoint. But cover every edge. So all you're doing is you're taking the complete graph and dividing it into smaller cliques so that you cover all the edges. And at this point, there's no matroids. This is really just a pure enumeration problem. And the question is, how can you enumerate? How can you enumerate this? And the reason you might suspect this looks like a design problem is that suppose instead of saying cliques, you just said cover with edge disjoint triangles. That's enumerating the number of Steiner triple systems, so some context there is necessary as well. So if you replace cliques then you get enumerating Steiner triple systems. And this was so the upper bound was done in work of Lineal and Luria. And so this is the lower bound, and the upper bound is due to, the upper bound is due to Lineal and Luria. And the lower bound is due to Kibosh in his breakthrough work. So really for us, there'll never be, because we're allowing cliques of size 2, it turns out that we'll never need really advanced techniques in what is known completion, but instead we're really concerned with sort of the upper bound technique. And what Lineal and Luria do is they use this technique called the entropy method. And really the main point of this paper is, one way of interpreting the main point of this paper is giving an entropy-free proof of their result that sort of naturally generalizes to this setting. And so yeah, so I'm going to basically just talk through the proof of this result in a certain amount of depth. If there are any questions on what I've said so far, right now might be a good time for questions. So if not, I'll make one simplification, which is not really necessary, but makes the argument a little bit cleaner. So let capital M equal 20. We will consider clique partitions such that every clique has size bounded by m. And I will mostly focus on the upper bound. The lower bound is more straightforward. So, and the reason we want bounded size is it turns out that there's a relatively easy reduction. It's not completely black box, but you can basically suffices to consider a clique partition where every clique is small. The reason is that if you have a very large clique, it turns out there are just many more ways to cover that large clique with a bunch of smaller cliques. So it suffices to consider this like bounded clique setting. And so now, given this, let's define a little bit more notation. So consider enumerating partitions where with SI cliques size I. So then we know that since these cliques cover the edges edge disjointly, we know that SI times I choose 2 is equal to n choose 2. So this is just encoding the fact that these cliques are edge disjoint and cover all the edges. And let f of S2 dot 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 SM be the number of such decompositions. And what in fact we'll do is give an upper bound for f of S2 of this function for every possible choice of S2 to SM. And they're like at most n to the m choices. And n to the m is like polynomial versus the thing we're counting is more than exponential. So it's fine to just sort of find the largest possible value. And so given this, it's kind of an abstract thing. The crucial idea turns out is that every clique partition has a certain amount of symmetry in it in some precise way. And so the crucial idea that allows us to replace entropy is the following simple observation. So consider a fixed clique decomposition. C with SI cliques of size I. So take a random subset of P times S2 SM of the cliques. C, and consider the edges and consider the remaining uncovered edges. And I'll denote this G of P. So I have a fixed set of cliques. I'm taking a random fraction P of them, and I look at the remaining graph. What does that graph look like? So it turns out that this graph looks random in a certain precise sense. It looks quasi-random. So in particular, so this is with high probability. So because a random choice of cliques, so with high probability, the degree in G of P of every vertex V is roughly what you expect. So we keep like a 1 minus P fraction of the edges. So what you would expect is the degree to be 1 minus P times N. And it turns out that this is true up to some error. So plus an error of O of N to the 1/2 log N for all V. And not only is this true for degrees, this is true for sort of co-degrees and higher. So this is maybe not the most standard notation, but let's say the degree of G of P of V1 through VK. This is just the intersection of the neighborhood of VI. So this is just the common neighborhood of these vertices. So V1 to VK. And I look at a set of vertices V, which are connected to all of them. So the probability you're connected to each vertex is like 1 minus P if this were a random graph. So you'd expect this to be 1 minus P to the K times N. And okay, you have a similar error term, N to the 1/2. Okay. For all K less than M. And okay, this will hold not only with high probability, this holds with probability, let's say. So let me just quantify it with 1 minus N to the minus 50 or something. You just need some sufficiently large power. So what this is saying is that your graph, once you delete it, it looks random in this very precise sense. It's this is often a notion known as typicality. So every fixed set of vertices has approximately the same number of like neighbors. And this would be true if you sampled a random graph with high probability. And that's why it's in some sense a notion of quasi-randomness. And so let me sketch the proof idea. Let's figure out why this is true for a single vertex first. So consider a vertex V. So there's this slight issue that I've sampled a random subset of a fixed size versus keeping each clique with probability P. Turns out that doesn't matter. You should ignore that. That's just an artifact. And you should just imagine that I'm keeping every clique with probability P. So let's look at this vertex. So its edges are in some cliques. So, okay, this is a clique of size 3. This is some clique of size 4 that contains its edges, some clique of size 3. And so I'm sort of deciding to keep each clique or not keep each clique with probability P. So the expected number of uncovered edges, well, I can just look at every edge. The probability it survives is probability 1 minus P. So this is like exactly 1 minus P times N minus 1. And in this case, if instead of sampling a fixed size, you just imagine you sample every clique with probability P, then this is just, it concentrates just by Chernoff. More generally, so concentration in this case follows by so that handles the single vertex case. It turns out it can be a little bit more complicated if you start looking at co-degrees. And the reason is the expectation is not exactly correct. And for this, there's kind of a simple example. So consider V1 and V2. There's this one edge between these two vertices. And so that the clique between them that contains this edge, well, whether or not I include that clique, it can delete some number of vertices, but they get deleted with probability P, not probability P squared. So consider some vertex V here, this edge, and this. So let me actually use different colors because So so I have the red edge and the blue edge. And suppose they're not in the same clique. The probability that they're included in this randomly subsampled graph, they're independent. So probability that this vertex V survives and is like a common neighbor is probability probability 1 minus p squared. And that's exactly what you expect. But for the vertices here, let's say V prime, which are in the same clique, well, it's only probability 1 over p, 1 minus p, because you just need to know that that clique wasn't deleted. But notice that this can, all of these special vertices V sort of have to be in this clique coming off V1 and V2. So it's only a small number. So long story short, there's the expected number of uncovered edges. Well, it's what you expect, 1 minus p to the k times n plus, okay, there's some O of 1 error. And the O of 1 error is handled by our error term above. And okay, and concentration in this case follows from a Zuma-Hofting, or if you're maybe careful, maybe you can use Chernoff. So that completes the proof of the key lemma. So all this lemma says is you take your clique partition, take a random sample, it looks random enough. Given, I mean, somehow this is a very simple observation, but it turns out what this lets you do is it lets you count a certain type of orderings. And in order to do that, we first need to derive some consequences of being quasi-random. So the first thing is to note that in any such graph, the number of cliques is approximately the same. So suppose the degree of G of P, V equals 1 minus P times N plus minus O. So the next step is, suppose I know that every set of k vertices has approximately the same number of neighbors. Using this, you can actually count the number of cliques in G of P. And the way to see this is that you can just build these cliques one by one. So the number of cliques of size k plus 1 in G of P, let's just build this out step by step. So I have a vertex V, so I have n choices for that vertex. Well, I need to choose a neighbor of that vertex. So they're at most, so like 1 minus p n plus my error term, a number of choices for the next vertex. And then I have to choose a neighbor of that vertex and so on. So you can just write out this product. And notice that I counted them with respect to an ordering here. In reality, I need to average out the ordering. So I have to divide by k plus 1 factorial. And if you just do it out, it's n to the k plus 1 times 1 minus p to the k times k plus 1 over 2, or k plus 1 factorial plus minus O of plus an error term. So what does this mean? This means that in any such graph, I know the number of cliques of any fixed size. And well, what this lets you do is it lets you, instead of counting decompositions, it lets you count a certain special type of ordered decomposition. So the key point now is, instead of counting f of S2 dot 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 SM, we count ordered clique decompositions. So it seems kind of strange. I mean, at least to calculate this is sort of easy. Well, okay. So the number of ordered clique decompositions one of these equalities is, so this has to be related to f of the function. It's just f of s2 dot 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 sm times the number of ways to order the cliques, which is just s2 plus dot 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 plus sm factorial. So I've really done nothing so far. The next idea is that we're going to, instead of counting all clique decompositions, we're going to count clique decompositions which are nice in some way. So by nice, I'm not going to give a formal definition. What I'm going to do is I'm going to kind of write down a bunch of properties which hold for almost every clique decomposition using our initial property, and then we're going to upper bound the number of such clique decompositions. So what I do is I divide into chunks. So in total, there's the sum of S2 to SM number of cliques. Let's divide them into chunks where each chunk has the size of S2 dot 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 plus SM times n to the minus c cliques. So like n to the 1.99 cliques roughly. And you have these cliques and you want in each chunk you have approximately, so what I mean by approximately here, you need to be slightly careful with, but SI times n to the minus c cliques of size I. And it turns out that if you think about this, all this is saying is that, like, if I look at the first half of my random sequence, roughly half the cliques of size I are in the first half and roughly half are in the second half. And that's going to hold for almost all orderings. This is just by the turn-off bound. So, okay. And the second thing I will need is that, so I have each of these chunks. So this is at some, call this time T1. So, okay, I'm going to refer to the ordering and time interchangeably now, but all I mean by time is where you are in the sequence. So I have I have each chunk. So I look at the first chunk, I plant those cliques, and now I look at the remaining graph. I want that remaining graph to always look quasi-random. So and what do I mean by quasi-random? I mean that you have precisely this property holding. And because this property holds with probability 1 minus n to the minus 50 or something, and I'm only bounding over polynomially many events, I can assume that this holds for almost all orderings. So the number of such orderings is like the number of total ordered clique decompositions divided by 2. So I've lost nothing by doing this, basically. And so now, okay, so what do I do? So first I need to choose the number of ways. So let's upper bound the number. Let's call these good clique decompositions, good ordered clique decompositions. Well, so first I need to figure out how to order the sizes of the cliques in each chunk. And that you can just do by Stirling. It's S2 plus dot 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 plus SM times n to the minus c times. So this is just in each chunk, I need to choose where to put the cliques of size 2, cliques of size 3, and so on. So I just do it. And okay, there are n to the c chunks. So that's the number of ways to order the sizes. And now predicted amount. So let me explain what I mean by predicted amount. What I mean here is, suppose you reveal the first like half of the chunks. Okay. And now I'm looking at this chunk. And I want to plant a clique of size 3. Naively, there are like at most n cubed choices for that clique, but that turns out to be too lossy. The way to look at it is, well, this clique I have here cannot intersect the first few chunks. And given that it can't intersect the previous chunks, and the fact that I know it's the previous set of chunks is quasi-random and the number of cliques in the remainder is fixed, I have a predicted amount. So since half of the chunks are before me, it would be like n choose 3 times 1/2 cubed plus minus O of n to the 2 point or n to the 5 halves log n. And so on. And so I have a predicted number of choices at this stage. And I can sort of just multiply out the number of choices. And because of how I've set it up, this number of choices in my upper bound is always going to be the same. And so now, okay, you have basically, you have to do an integral and use Stirling's formula. And if you rearrange, what you find is that, okay, so I'm hiding just computation, but slightly annoying computation. You find that you get an upper bound on the log of f of S2 to Sm. So in particular, you get that it's at most the following sum. So Sk is what it was earlier times log of n to the k over k factorial minus Sk log Sk plus Sk minus n choose 2 plus some error term. So you get some upper bound. And now this is the left-hand side is just a continuous optimization problem. And if you solve it, it turns out the optimizer is essentially S3 equals n squared times square root of 3 minus 1 over 6. And S4 is n squared times 2 minus square root of 3 over 12. I mean, this is, you do this by doing Lagrange multipliers, and SI equals 0, 4. I not in 3 and 4. And plugging in gives the bound. So essentially, to prove the upper bound, what you do is you consider this ordering, and noticing the fact that you're quasi-random at every stage, you get an upper bound for the number of choices. Now, I did something, and okay, I derived an upper bound, and I claimed that this bound was sharp. But why? Why is this bound sharp? And sort of why did we know this bound was sharp before we did the computation? So it turns out there's an easy way to sort of reverse this bound, reverse the lower bound. So to reverse and get the lower bound, consider the following process. So you have your so start with Kn. For basically the maximum number of steps. So I have to explain why I have to lose something in a second. So with probability, either S3 over S3 plus S4 look at your remaining graph. And choose a random triangle. Else with probability S4 over S3 plus S4. Look at your remaining graph and choose a random K4. So what am I doing? I'm looking at my complete graph. I'm flipping a coin with the right probabilities. And if I get that I should plant a clique of size 3, I plant a clique of size 3. And if I get I should plant a clique of size 4, I plant a clique of size 4. And now, if I tell you that you have to plant a clique of size 3, and suppose I tell you a fraction p of the edges have been covered, the number of choices for that clique is exactly what I had because of this quasi-randomness prediction. So as long as you believe I can run this process, then this sort of automatically gives you a way to reverse the lower bound. So somehow before I wrote the proof, if you know this fact, you somehow before you write the proof, you know that the bound is reversible. And that's what's happening. Now, it turns out that analyzing this process, it can be done. It turns out this is actually more difficult. That it turns out if you want to use known results in the literature, you don't do this. You can instead take S3 minus n to the 2 minus delta triangles first. And then take S4 K4s. So instead of like sort of randomly doing S3 or S4, you can sort of do the triangles first and then the K4s. And this gives you, once you remove the number, once you account for the number of orderings, it gives you the same number of ways. And this follows from known results on what's called the triangle removal process and the K4 removal process. You just count the number of distinct outcomes and that's it. And yeah, so that's actually all I had to say. So that's all I had. So thank you, and any questions?
Awesome. Thank you so much. Let's do a round of applause if everyone could unmute, and then I'll count to 3 and then we'll clap. 1, 2, 3. Excellent. And does anyone have any questions for Mehtaab?
A very vague question, but so there's this big difference between rank 3 and then 4. So with the numbers, like 4, 5, 6, all the rest are the same. So what is it that goes right or wrong that causes that change?
Okay, so I can do this. So if you can actually just rewrite, you can write this proof. So if you replace covering a graph, the complete graph with the complete multigraph with like cliques and simplices, you can actually reprove the other result. Where this nasty number comes from is sort of, there's kind of a magical numerical coincidence that happens. I can explain what it is roughly. So the way to see it is the following. So the function you end up optimizing is sk times log nk over k factorial. So it's this up to some absolute constants. And let's make, so it turns out that if you want your sk to contribute, you want it to be like ck times n squared. And we also have one other constraint, which is that sk times k choose 2 equals n squared over 2. So if you plug this in to leading order, so to leading order this optimization, what it comes out to is something like, I need to remember. So it comes to sum of sk times k minus 2 times log n. So this is on the scale of n squared log n. If you want to just, you just want to be that accurate. So now this is, so this is now a linear optimization problem. This is, you have a linear objective function in terms of a linear constraint. So let me write this out more explicitly. So this is like S3 plus 2S4 plus, 5 or 3S5 plus dot dot dot. And the objective, the constraint is something like S2 plus 3S3 plus 6S4 plus 10S5. And so if you look at this, the most efficient place to put values are S3 and S4, because the ratio of the coefficient here to the coefficient here is a factor of 3. And if you place it on S5, it's larger. So you essentially want to put, in the optimization problem, put no mass on S5. So this is the numerical coincidence that causes you to want some cliques of size S3 and some cliques of size 3 and some cliques of size 4. For the higher values, if you write out this optimization problem, there's no such numerical coincidence. Yeah, it's kind of a very concrete thing, but I don't have a more highbrow explanation.
Oh, that's a good explanation.
Excellent. Does anyone else have a question?
I don't have a question, but I just want to say that I'm really impressed. I mean, Jorn and Remco and I, we had a long fight with R equals 3. So I know it's hard. So thank you for doing this, and it's great.
Thanks.
All right, well, with that, I think I'll end the recording and then we can have some informal discussion. Thanks again, Mehtaab.